All right, what is this? We are not eye surgeons or eye doctors, but what this is supposed to represent is that we care about perception, audiovisual perception, and a lot of humans just perceive the world through perception. And the mission of our company is kind of to try to enhance technology or create technology that transcends your expectations from the technology. So basically, I have a very simple example here. So this might be an image that you receive through some maybe whatever technology, and this is this image. You see it's lacking a bit of detail. It's very kind of darkish in the background, not really black. You don't know there's something maybe. The fire is not really precise. It's very light. So what we try to do is to get you to have this kind of experience. This is visual. We in Stockholm do sound, so we do not do so much visuals, but it's maybe easier to understand visuals in this case. A bit of history of Dolby. So Dolby was founded in '65 by Ray Dolby in London, although he was an American, and it's actually an American company. The very first, I think, technology that was sold in '66 was the noise reduction technology. I think this is what made Dolby known in the first place. And the thing I'm going to talk here about a little bit is the Dolby Atmos technology, because my talk is about object-based audio coding. And this is a technology, a cinema technology that represents sound sources as objects, distinct objects, not in channel format, which allows a certain advantage of the previous technologies that were there, like surround. And maybe one highlight is in 2015, we received Academy Award. It's not the only one, but that's one of the recent things. So about the company, the headquarters is in San Francisco. This is the newest office. This is the headquarters. It's quite big, the building. We have more than 700 scientists and researchers, research engineers. We're big, but not too big, so we have something like around 2,000 employees worldwide. We have 49 offices in 21 countries. This is just the two offices. San Francisco is over there. It's in the United States and California, as you might know. And the Stockholm office is over there. So we're in the northern hemisphere, not that's up north, but still we're there. And we're actually the biggest, as of today, we're the biggest research group within the whole Dolby company, actually, our small office. So we're a bit less than 20 people actually there, but most of us are researchers. Yeah, a few more numbers here. So Dolby does own a bit of patents. We have a big patent pool. So as I previously mentioned, we have 15 Emmys and 12 Academy Awards won over time. Not necessarily for the acting performance, but for the technical contributions that made the movies and stuff possible. And there are like 35,000, maybe more, motion pictures that were released with Dolby, using Dolby technology. And the former Codex Theater, where the Oscars are given out. Today it's the Dolby Theater, so it might help us get some more Oscars in the future, maybe. So this is more or less the product line that Dolby has, where Dolby is active. Dolby is not a pure sound company anymore. So we do vision. Dolby Atmos is the cinema sound, 3D sound reproduction. We also started to build cinemas, actually, where we put our visual and sound technology and optimize it. So we optimize the experience in our own cinemas. We have some basic audio processing technologies, which goes under Dolby Audio. And we do have some Dolby Voice products, mostly related to teleconferencing systems. And today I will just talk a little bit about Dolby Atmos, as I mentioned before, relates to the object-based audio case. So there were some audio challenges before in the cinema, where the audio was played back in some 2D surround format. So it was only in the horizontal plane, so the sound mix could be compromised for some sort of sound scenes. And maybe sometimes the output might have been unnatural. And what, of course, the biggest challenge is that once it is in a 5.1 channel format, you can only play it back consistently in a 5.1 playback system. And with object, which is you can position everywhere in space, you can actually render it to any type of output format and adapt it to any type of reproduction facilities. So here again, there were like studies of how can we represent this kind of 3D audio scenes in the more natural ways. This is kind of the science behind, and then we come up with some technology which is then kind of object-based. So every sound source within like a movie piece is considered as actually a point source in the actual realization. And what this allows is that you can move these sources very precisely in a 3D room, and you can represent this 3D scene over any a playback system or whenever any speaker setup in a cinema. So how's the Atmos technology doing? So in the cinema, there are a lot of screens all over the world using this technology. So if you go to a cinema, if you like movies, you probably heard of Dolby Atmos. There are mixing facilities that do produce content with Dolby Atmos, and there are like more than 700 movies, I think, which use Dolby Atmos already. Also, you can have a sort of Dolby Atmos experience for the whole home cinema, usually conveyed on a Blu-ray disc. And there again, a big number. So we're gaining momentum. This is a new technology. We expect it to be bigger and grow over time. But this is where it's right now. OK. So much for PR for Dolby. This is a bit of a more technical outline of what I want to present to you today. I have been working previously on some object-based audio coding, and this is going to be the second bullet here. This is my previous work, which I did with the Bordeaux Computer Science Research Laboratory. And depending on how time goes, I will also show some technology from Dolby that I was involved in as well in the last 2 years. So first, maybe let me explain like a little bit of a differentiation between what is object-based audio coding and maybe spatial audio coding. So in object-based audio coding, so you have each sound source is an object maybe, basically. And it can be just a pure sound source, or it can be just a group of sources. It could be like a whole section of violins, for instance, in a recording. And it's very much similar if you're familiar with sound engineering, that you have several tracks, and each track represents kind of some audio source, and so you can think of this. And there have been already standards in the past which were applicable to object-based audio, such as the MPEG IMAF standard, and one particular aspect of this is that each source was coded separately before transmission. And spatial audio coding, what it actually tries to do is that instead of coding each sound source in a 3D environment separately, you try to group the sources and then to gain some coding efficiency from this. So some examples for this of data reduction is, for instance, if you have, let's say, 10 audio sources in space, and you play it back over a stereo system, it is already some sort of a data reduction. When you go from object space to channel space, you reduce from 10 objects to just 2 channels. So you have gained basically 8 audio streams. 5.1 surround is another one. It is related to parametric spatial audio coding, just to mention here. You might know it, maybe not, from some MPEG technologies deal with parametric spatial audio coding. Here it's a bit something different. So the problem is actually when you have a certain number of audio sources and you have some sort of a mixing procedure, how to put them together. So you want to go from a higher dimensional signal space to a lower dimensional signal space. And then you want to go back to the original signal space again. And of course, in between, you will have some losses, and you want to minimize these losses, and you want to control these losses such that these losses are perceptually well, indistinguishable practically from the original sources. And well, to put it very simple, it creates some sort of an underdetermined linear system of linear equations or nonlinear equations. which you kind of solve in one way or another. So just to explain a little bit, so this was my previous PhD work, partly where the problem was to, we wanted to enable active music listening, which means that usually you have some audio like on a CD or something, and you just can play back this audio. You can listen it, you can skip it, goes to something else. But we wanted to see if we could enhance this experience by personalizing it and giving the user the opportunity to change the composition of the audio, to do something within the mix. So, so this is just a description of the entire system. So just imagine you have a band to the left-hand side, and you record this band, and ideally you would have a recording of every instrument separately, and this would be an object that you consider. Then you create some artistic mix out of this, which you can play back on a stereo system, for instance. And then this is kind of the coding, decoding part. You want to reduce this data rate before you store it as a bit stream, so that you can store it as in a file format or stream it. And then on the decoder side, you want to take this bit stream. You want to go back from your down mix to the original objects, and then you can allow personalization that the person, like a user, can remix this original sounds and then render it, for instance, a binaural mix, and listen to his own mix. So this is the general chain. And of course, where comes the audio object coding aspect into this is, of course, these two steps. And the highlighted here is encoding and decoding. So this is like a block diagram, very visual, of such a system, how you can realize that. I will just go very quickly on and mention just some aspects. So here you have the actual objects. So every one is just a single channel signal you can imagine. You would process these signals in the short time Fourier transform domain, for instance. You would use some knowledge of the hearing system that, for instance, that we do not, our brain does not process the hearings like in a linear, but more in nonlinear bands and stuff like that. So this is more or less a coarse description of the domain where you operate. And with these objects, what you can do, you can here first just generate your artistic mix. So like a CD where you can listen to this music. This would be generated here. So there is some sound engineers behind who kind of have some mixing rules and create this mix. And the system, this coding system, what it actually does is all the aspects here. So knowing this rule, it would do some sort of analysis, and it has some aspects of quality control. It's the quality that you want your decoded signals to be. And you can model these signals, for instance, as a Gaussian mixture model in the very basic case. And you can define the quality here as the signal to interference ratio, where one signal is one object of interest and the interference would be all the other signals. Then you could create additional channels, additional audio channels, or observation in this case, which you would compress. So this piggy bank actually means that you make savings here. So you could use some MP3, for instance, encoder here to reduce data even more, and then you would have two streams, one side information stream and one down mix that you can listen to, and this is what you would transmit as your actual raw data. So maybe one interesting aspect related a bit to the talks that were already done today. So this controlled mixing here can be realized with the mathematics known from phased array, for instance. So what you can think of here is that, and you don't have here any physical losses, such as you would have with antennas. You just can use the mathematics behind to do some sort of beamforming here. And you can play with the spatial resolution of your virtual array to do this kind of controlled mixing. And on the decoder side, you would take this bit stream, you would separate it into the down mix that you can listen to on a conventional stereo playback system. You have this additional side information consisting of extra observations, extra channels, some mixing information, metadata, this same channel data, and then you would take all this together and recreate the original objects from this. So in the literature, this problem here, this block here, you will also find termed as informed audio source separation, for instance. So you have some audio sources here, and you have additional information, and this allows you to do some sort of controlled upmixing. And this upmixing, if you work with phased array, at least the mathematics foundations of it, this would be, for instance, the optimal filter coefficients to get from all this, having this information. So this metadata could be, for instance, the ideal model parameters of a Gaussian mixture model, like variances, and the spectral distribution of the variances, like the power spectra. And then you can get you back to your objects, and this would allow you then to do whatever you want with this object. Just a bit, some properties of the system. So it supports, the systems I have implemented like 2 years ago, and we had a demonstrator for this. And so the supported objects were single channel or multi-channel. And of course, if you design such a system, your perception metric that you want to use, it should be spatial first if you use, for instance, like a phased array, for instance. And this could be, for instance, your array gain, or any similar sort of metric. And you should not forget, because we're working in the audio domain, that you should have some sort of perceptual weighting or aspects of this to be sure that when you, well, what you predict as quality kind of matches with the human perception. Yes, this is maybe not so important. So the system actually supported, or still supports, 3 modes. You can generate just an artistic downmix, and then try to generate your objects, get your objects from the downmix, of a stereo downmix. You can create synthetic downmixes where you create a downmix in the mixture space, which you cannot necessarily listen to, but it's some optimal, according to some mathematical criterion. Or you can use a hybrid mode, and then you can do both. You can listen to this mix, and you can generate data in an optimal way, which allows you a certain degree of quality after the demixing. Yeah, maybe too much of details. And what are maybe the main applications for such a system? It's music publishing, for instance. You could just imagine that an artist, when he creates his music, just not provides you just a stereo downmix, but also has this additional information, the side information that can be stored on a separate server or somewhere. And if you have the dedicated software which understands this additional information, you can either just play back the rendition that the artist gives you, or something that you buy today, or you can have a service which provides you extra information from somewhere, and then you can use this information to unmix the rendition and create your personal mix out of this. It is, of course, 3D sound related. You could use this technology in some VR, AR environment, where you can adapt. So this would be kind of the personalization, where if you put yourself in a virtual environment, at every time instant, you have to adjust the sound scene according to your position within this space. And then you need some sort of means to be able to re-render the content of this. All right. Maybe a few words on some similar coding technique, but the original purpose might have been, or the motivation might have been a different one. So I've been talking about Dolby Atmos before, and this is a cinema technology. And in the cinema technology, and when you produce a movie, you make a movie, you usually have more than 100 simultaneous objects that appear in a sound scene that make it very complex. So it's obvious that if you want to reproduce kind of the cinema experience at home, you don't have, and you have like a lot of speakers like 11.1 or 11.2, 22.2. You cannot just, it's too much data for the home environment. Also, it's too much data to transmit or to store on a Blu-ray disc. So you need a codec, you need something to reduce this amount of data, but still what you want is, you want to preserve this kind of artistic intent, because the artists or the people behind the creation of these movies, they have an intent. They want you to perceive a certain scene, what it looks like, how it sounds like. And you want to preserve that when you go from the cinema to the home. And so, So the Dolby Atmos system, what it actually does, it splits the audio scene into two types of channels. You have like a static bed channels. It's the scene that doesn't change. It's like the constant playback. And you have dynamic objects which can move around in space freely and change their position. And it's rendition agnostic. This is very separate. This is what I said before. You do this independent of the playback format. Yes, and what the codec is supposed to do at this point is it is intended to preserve this intent, but it is also supposed to provide a low bitrate and low decoder complexity, and this is the difficult task of this. So you want the same as here, with as little loss as possible, so that the user at home can feel like he's almost in the cinema, actually. I don't know if this is the slide. Is this the slides or is it the PDF? Because this is a little video, just to show you how the object would move in a realistic 3D scene. But that's no, that's not. That's the video. No, that's it. No, is it? No, close this, please. Close this, please. No, it's the PDF. Okay, then just open the PDF. Open the PDF again, please. All right, so we do not have a video here. It doesn't matter. So again, very briefly, so this is very similar to what I have shown you before, but it has some specifics which are very little different. So you have against your objects, you try to downmix them, you create a lower dimensional downmix, you have some object metadata, which is like their positioning in space. And then you would have what is called here the JAWC, so Joint Audio Coding Encoder, which kind of creates you the upmix parameters, so what has been before the additional site information, which you then put everything together in the bit stream. And on the decoder, again, you have your downmix signals, so lower dimensional signal space. You have the extra parameters. Use these parameters to go to a higher dimensional signal space, which are, of course, only approximated. And you can use the object metadata, which is the positioning, to re-render it according to the scene. So with the codec, what you actually want to realize is such a system. You have your objects, and this is what's happening in a cinema. Like 100 signals here, every signal has a positional metadata, and you just put it to a renderer, and then you can play it back. So here in between, you just have elements to go to a lower dimensional signal space. Some properties of the Dolby technology is, for instance, so you can, in between, you can reduce the number of this 100 objects to some 11, 15 objects, change their locations, which is shown like this. So you do some sort of clustering here, and you can then work with less signals in that case. Some other things, maybe something that's worth mentioning is this property. So if you consider each object, so original signal, as independent from each other, which is a valid assumption in a Gaussian mixture model in this case, when you go to a downmix to a lower dimensional mixture and then you upmix from a lower dimensional mixture, you introduce correlation between these objects because they come all from the same source. And there is technology in Dolby's AJAX system which kind of does some sort of decorrelation. And this technology, at least mathematically measured, is that the correlation, the cross-correlation between the objects of the original objects and the decoded objects is the same. Why is this important? Because if you have correlation between objects in your rendering, the spatial impression of your object will collapse. So if you have a source there and they're independent, you will perceive two sources. But if you introduce correlation, they will move closer together to the middle. And this you don't want to avoid because you want to represent the original sound scene as much as possible. And of course, it's flexible in the rendering. So if you have like a 3D cube, it depends on your speaker layout, and then you can create a mix that corresponds to your system. So where would you find Dolby's AJAX coding system? It's been, so the Dolby DG+, Dolby Digital Plus encoder, if you're familiar with that, it's a channel-based coding system. So the joint audio coding extended the channel-based system, which supported objects, and you will find this in certain AV receivers, which do allow you a certain audio playback with objects that can be re-rendered. And there is also the latest AC4 coding standard that was standardized, I think, officially this year by ETSI. It's audio coding 4, so it's the latest Dolby coding for all kinds of immersive 3D and backward compatible coding. It's more efficient than the previous one, for instance, so it has some improvements in here, and with this one, for instance, that's the bitrate that you usually have, like with 256 kilobits per second, you kind of can represent a rather complex sound scene, and this is what the technology allows you to do. And that's pretty much it for me. I think the 5 minutes are not over yet. I had a little video for a teaser for if you want to see that. Yeah, okay. Now you can play the video, please. Yeah. So this is related to my first project I did with the university, which kind of illustrates a little bit what you want to do. So just imagine you want to change, for instance, a position of a source. You want to pan it between left and right. You want to change its frequency. You want to make it louder or softer. And for this, what you don't want to operate on the mix itself, you want to decompose the mix into objects. And so in this case, then you can mute, for instance. You can just play back only certain elements of the mix, and you can do all this transformation that I mentioned before on the separate tracks. And this is the sort of which you achieve some sort of personalization. Of course, you can then, if you have object-based audio, you can render it and use it in different scenarios, even in cars, if you have some 3D system in car. So the system is downward compatible, as I said. You can just play back the stereo or listen to your own mix. This is, again, a summary of what has been presented before with in some more detail. Well, yes, that's very much it. I hope that's it's been interesting to watch for you. So thank you very much, JB. Thank you.
Okay, we have time for one question, maybe. Darli, please, the microphone for him. Okay, I can give this one.
Yeah, thanks for the great talk. I have here 2 questions which were sent by internet from a colleague of mine who's watching your presentation at YouTube in the University of Campinas. Okay. So his questions are, first, it seems like audio object coding will be the standard for spatial audio coding. So he wishes to know if you agree with that. And from your perspective and the perspective of Adobe, how can the academia contribute to the development of spatial audio object coding and spatial audio as a whole?
That's difficult questions. I mean, for the scenarios that I presented, it might be the future object-based audio allows you to do certain things which you cannot do by definition with channel-based audio. But the transition is still slow. So for instance, we at Dolby, our first deliveries are going to be hybrids. For instance, for broadcasting, which support channel-based audio with a few objects on top of it to allow a certain degree of personalization. So for instance, we have a collaboration with British Telecom, and I think they already show, or they offer the premium experience to watch the Premiership, the Premier League, the British Premier League, with personalized kind of commentary and sounds in the background and everything like that. So this is like the first steps. The question is, of course, it's a question of how the audience is going to accept that, how the industry is going to accept that, and that is going to be influenced a lot by this, how the adaptation of the industry is actually. Because we're a technology provider. We're not like a hardware manufacturer, so we can offer things. We cannot really influence it, but we try to have initiatives to help content creators create more content, which is object-based, so there is more options for the user to experience from that. And your second question, how can academia contribute to that? You can. Of course, it's a bit of business. So I think we had this talk from, I don't remember, like one of the morning talks on this ITUT contribution, I think it was. So where they successfully proposed something that was adopted. I think in general, there can be contributions from the academia, which make sense. Of course, you have to consider that it's not going to be necessarily evaluated to the academic excellence of the contribution, but more of the pragmatism of the solution. So in basic terms is that, can you be more efficient? Can you improve the quality of the sound? So something that the user, in the end, will actually be able to appreciate. So our focus as a company, like I said, in industry, we want to provide technology to enhance the experience for the user. It's not necessarily about the formulas behind, right? So if you want to contribute to this field, there have been contributions still, but I think there are still open things. For instance, the first system that I showed you, there are still possibilities. How to do the controlled mixing, for instance. I mean, I did one thing, you can maybe think of something better. So there are contributions for academia that are possible. Of course, in terms of collaborations with industry, it's a bit trickier, a bit more difficult in general, of course. Yeah. Okay, so thank you very much again. Now just some minor information. So today at 8 p.m., the bus will be waiting at the hotel so that the invited speakers can go out for the dinner, right? So the bus is going to stay.